Welcome to another fabulous edition of Comet Algebra. This video is for Algebra 2, Chapter 6, Section 6. It's called Factoring Polynomials in your book, but I entitled it Synthetic Division in Factoring. And this is also known as the three theorems. First, let's look at a very mathematical definition of a polynomial. It can be written in the form where a to the n is just a coefficient of the n term. Like, don't let this definition scare you. If I go down here and look at this g of x, in this example, a of n is 3, and the first n, is a third. So that's just the first term. And then this a to the n minus 1 means we're just going down 1 degree. So we're looking for the x squared term. So in our example, a to the n minus 1 is a negative 4, and this is an x squared because the exponent came down 1. And it just keeps on coming down until it reaches, we have like an x term, and then this constant is, let me put the x term in here, plus 2x. And then this constant, this is really to the 0 power, like this negative 8 is really negative 8 times x to the 0 power, which is 1. So don't let this definition scare you. These are just subscripts denoting that the powers are descending, and this one is called our leading coefficient. I refer to that quite often. And you need to know that the degree of the polynomial is the highest exponent. So in the example that I chose here, this is a third degree polynomial. And where that's going to come in handy pretty soon is the degree gives you the number of answers you're looking for. Also note that part of this definition is that these exponents, they could be 0 or they're positive whole numbers. In other words, polynomials are not written with negative exponents or dividing by x. And polynomials also have real numbers for these coefficients. To lead us into our first theorem, we're going to do a little comparison. We're going to start with this polynomial, and we're going to compare the value when we plug in 2 for the x, and we're going to divide this function by the factor, which is x minus 2, and we're going to compare that remainder. So I'm just going to do this sort of quickly. So first, looking at g of 2 and plugging a 2 in for the x, I get these values, and 24 minus 16 plus 4 minus 8, I end up with 4. So now let's do the division. I chose to use synthetic, so since the factor is x minus 2, I put the root in of 2, and then doing the synthetic quickly, let's check and compare what we get as a remainder. And 12 minus 8 is 4. And this was discovered and is very useful, that when you plug in the value of the root right here and you plug it into the polynomial, you get the same thing as if you divide the polynomial. And this leads us to our first theorem. The remainder theorem says that if you divide the polynomial by a binomial of x minus a, where a can be just any number, the remainder that you get from your division is the same as if you would have plugged in that number to the polynomial. This is very, very handy. When you are asked in a problem to find the remainder, you can use either method. Some people prefer the synthetic and will go ahead and do the division, and some people will plug it in. We want to be able to use both when they're convenient. The next theorem to discuss is the factor theorem, and this is a bit Captain Obvious. The factor theorem says that if you have a binomial, x minus a, where a is any number, a binomial is a factor if and only if, when you plug it in, when you plug in this number, you get a remainder of 0. And that makes sense because if it divides in there evenly, the remainder is 0. And also makes sense because at that number, that's where the graph is going to cross the x-axis. So it'll divide evenly. No matter how I say it, this is pretty obvious, so please know the factor theorem. The rational root theorem is a little difficult for me to explain, but it's very easy to use. So I rewrote the definition of a polynomial, but I used capital letters for their coefficients. And the ones that we're interested in for the rational root theorem, we are only interested in the leading coefficient, so the coefficient on the highest term, and we're interested in this constant. Now the rational root theorem is just going to give us a list of possibilities. Our answers for the polynomial are going to be inside that list, and we'll have to check them. So your book uses this p over q, so I'm going to stick with that, where p is any factor of this constant, and so we usually have a list of these. So this is where the small letter p comes from. Q comes from all the factors of this leading coefficient, and we'll make a list of those. And then we have to, I'll put the Q here, all the possible answers, we could put all the different factors of C over all the factors of G. And like I said, we'll start making these lists, and it sounds a little complicated, but it's not. So let's look at example 1. We're going to make a list of everything that could possibly be an answer. In this case, we're not going to figure out which ones are the answers, but let's just make the list. So these factors, I'm going to call them P, all the factors of 10. All the factors of 2, we're going to call that Q. And we have to make a list of all the P over Q factors. And please keep in mind, when we're making this list, we have to include all the positives and all the negatives. So let's list the factors of 10 here. Plus minus 1, plus minus 2, 5, and 10. That's a complete list of all the factors of 10. And 2 is a nice short list for us to look at. So the Q values are just plus minus 1 and plus minus 2. So now to put our list together of the P's over Q's. All of these can be put over 1, which just gives us that list. So 1 over 1, 2 over 1, and so on. So all of these are possibilities, and then we take all of these and put them over 2. So that gives us some additional plus minus 1/2. Okay, 2 over 2 is 1, and we already have that in the list, so that's done. Another thing it adds to the list is plus minus 5/2. And 10 over 2 is 5, and that's already in the list. So this is the complete list of all the possible roots for this polynomial. And in a bit, we're going to go through the list and decide which ones work and which ones don't. Now we're going to use these theorems to help us factor something that there's probably no way you could have factored this before. Now remember, we're not looking for the answers, we are factoring. So first we're going to make a list of the possible roots. Remember, all the factors of 6 are possibilities. So let's list those. And thankfully, we have a leading coefficient of 1. So if we put these all over 1, this is a complete list of possibilities. Now we're going to use this factor theorem to see which ones of these work. Remember, the factor theorem says if we plug it in and we get a value of 0, that means it's a root. So let's start plugging these in. And when I plugged in a 1 to this polynomial, we got a -3, so that didn't work. We tried a -1, that gave us a -15, that didn't work. But when we plug in a 2 and we do the math, we get 0. That means 2 is a root here. So remember, one of the benefits of synthetic division, it brings the equation down a degree. So now it's a 3rd degree. If we do synthetic with this +2, we're going to bring this down from a 3rd to a 2nd degree. So let's do that synthetic. Remember, we do use the root in synthetic, so I use the 2. And this had to happen. We had to get a remainder of 0 because we know that 2 was a root. And what we've given ourselves here, now we have a new equation. Now we are down to an x² equation. So we have, in our factoring, we do have a factor. If the root is -2, the root is +2, the first factor we have is x minus 2. And I'll just write this so you can see that we have factored this this original polynomial, we've got it down to these two factors. And then we keep going if possible. So we have to look at this quadratic and see if it factors. And since it does not factor any further, you are done. This is the factored form of the original polynomial. In example 3, we are only asked to find the remainder when this polynomial is divided by this factor. Your choice, you may use synthetic or the remainder theorem. I think I'm going to choose the remainder theorem for this example. So just to remind you, the remainder theorem says if you take this factor and plug in the root of -3 and do the math, plug it in for x, what you end up with, your answer is the remainder. So I'm just going to do the math here. After I do all the simplifying, I end up with a -42. So that's what you should get if you had used synthetic. That would be the remainder. In the next example, you're asked yes or no. Is x minus 3 a factor of this polynomial? Well, we know from the factor theorem that if you plug in the root, which in this case would be 3, if you plug that in for x and you end up with a remainder of 0, then we can say yes, it's a factor. Or you could go ahead and use synthetic, your choice. But again, I'm going to start getting used to using these factor theorems. So I plugged in a +3 for x, and doing the math, you can see here that yes, this does add up to 0. So we can definitely say yes, this is x minus 3 is a factor of this polynomial. In example 5, we're told to factor completely. So remember the steps. We make a list of possible roots and we find out which ones work. So for the 1, I guess the only factor of 1 is plus minus 1. And then 2 is 1 and 2, so we have to put this 1, remember the p over q, gives us another possibility of plus minus 1/2. So this isn't too many to check. So we're going to plug these in and find out which ones of these give us an answer of 0, and then we know it's a factor. Plugging in a 1 gave me a 4, so that didn't work. But when I put in a -1, I got 0. So we have a winner here. That means that x plus 1 is a factor. So we found our first factor. Now we need to bring this third degree down to a second degree, so let's do synthetic with the -1. So the results of the synthetic now give me a quadratic or an x² equation. And now I need to take a look at this and see if I can factor it any further. So I'm going to put 2x² times -1 on top here and x in the bottom, because I'm going to see if this can be factored by grouping. And I do get that 2x times x, a negative x rather, when I multiply I get this, and when I add I get x. So I can rewrite this now, and remember in grouping you're writing the x a different way, writing that middle term a different way by writing it as 2x minus x minus 1, and then we GCF the first two and GCF the last two. Or if you prefer, you can use the diamond box and you'll get to the same thing. So now that I have the GCF of x plus 1, that is a different x plus 1 than this one up here. So I need to include that, all the factors here. So I have my first x plus 1, which I found right away up here. And then I have the x plus 1 that is my GCF here, and I'm left with 2x minus 1. So now we have completely factored this polynomial by using these theorems that we learned, and this would not have been possible without this knowledge. I wanted to do one more example here just to get refreshed on factoring by grouping. Now this is already ready to factor because these two have a common factor of x², so we're going to factor that out, and then we have x minus 5, and these two have a common factor of -9, so let's factor that out. So now that I've done the GCF on the first two and the GCF in the last two, I factor out their GCF, which is x minus 5, and I have x squared minus 9. And from Algebra 1, we recognize this is the difference of two perfect squares, and we can factor it further to x plus 3, x minus 3. So I don't know, maybe we need a little more practice in factoring by grouping. One last factoring example. Let's make a list of all the possible roots and see if we can find one. The factors of 4 are plus minus 1, plus minus 2, plus minus 4, and luckily we have a leading coefficient of 1, so these are the only ones we need to check. The first one I plugged in was a 1, and it worked right away. So we already have a root. So let's do synthetic with this positive 1, and we're going to bring this fourth degree equation down to a third degree. Okay, so that worked nicely. Now I'm down to a third degree, but I need to go further. I need to find another root. And so if we plug in a negative 1, let's see what happens. So putting in this negative 1, remember negative 1 squared is positive 1 times 5. Anyway, we end up finding another root, which is great. We need to take this third degree and we need to bring it down to a second. So we're going to do synthetic again, and we're going to use the negative 1. Be sure to keep track as you're doing this of the factors that you have found. This root of a positive 1 gives us a factor of x minus 1. This root of a negative 1 gives us a factor of x plus 1. But we're not done yet. Now we have this quadratic here, which I can write as x squared minus 4. Well, that factors really nicely into x plus 2, x minus 2. And now we have completely factored this polynomial. All right, that's what you need for section 6.6, so have fun with math.